Hi guys, we're back at it and moving on with more derivatives. So I was happy with the exam that it was a nice checkpoint for you guys to see if you understood where you were at or if you needed a little bit more review. So now we're moving on with something called higher order derivatives and derivative tables. Higher order derivatives is exactly what it sounds like. We're literally taking a derivative, which is a rate of change, and then we're going to take another derivative and the derivative of that derivative. That's what higher order derivatives are, is when we take an original function, let's call it y, and when I first take the first derivative, we note it as the derivative of y with respect to x. If I take the derivative of again, so this is what we call my first derivative. And right now we're just talking about notation. If I take the second derivative, the derivative on that first derivative, the way that we note that is the second derivative with respect to x twice. So that's the notation for the second derivative. And so on if I take the third derivative. The third derivative is just going to be the third derivative with respect to x 3 times. All right, so that's really important because what's going to happen is they'll say find this, and you'll have to know by this notation that they're looking for the third derivative. Now, if the original function wasn't in y equals form, let's say it was originally given to you as f of x, well then the first derivative is f prime of x. The second derivative is f double prime. The third derivative is f triple prime, and so on. Now you might be saying, why do we need to know this? And I keep on telling you guys that this year, unfortunately, is just the year of the mechanics. You're learning how to do everything, and next year you're doing more of the application. But just to give you a quick insight of where it's going, a lot of times we see position as our original function. So if I said, the height with respect to time is given to you by some certain function, I call that position. But now if my position changes, or just even thinking about driving, so if I say, oh, my position at a certain time is, and I give you some formula, if I take the rate of change on position, that means my first derivative of position, my rate of change on position is velocity. Right? If you think about that, I'm going 55 miles per hour on the highway. That's a rate of change on my position. Now, what if I make a rate of change on this rate of change? So for example, if I'm doing 55 miles per hour and then I go ahead and speed up, I'm changing the rate. That's talking about acceleration. So just so you know, there's why the higher order derivatives is really important, because they will eventually represent ideas such as position, velocity, and acceleration, which is a big topic in AP Calc. Okay, so let's practice. And I'm just going to warn you, this video is definitely going to be cut into 2 because there's a lot to talk about today. Okay, so hopefully you printed out the worksheet or did what I did, with just copied down the problems. So here, for the first one, if I ask you to find the first derivative. Okay, well that's not so bad. You just use the power rule. The 5 comes in front, you get 3 fifths times 5, which is just 3, x to the 4th plus 12x squared plus, whoops, I should have brought this up first, x to the negative 1. And then I take that, so it's going to be negative 1/2 x to the negative 2. So that's my first derivative. If I was going to actually ask you to submit your answer, you wouldn't do it like so. You'd bring that x to the negative 2 down because we didn't start with a negative exponent, so we shouldn't answer it with our negative exponent. However, if my question here was find the second derivative, well then I'm not going to rewrite this. I'm going to leave this like so, and I'm just going to keep on going. Here comes my second derivative. It becomes 12x to the third plus 24x to the first. This negative 2 gets multiplied to this to give me a positive 1x to the negative 3. And last but not least, if I want the triple. Now I can keep on going, All right, and at times you'll see you'll just end up at 0 when you just start getting to constants. But here, my third derivative would be 36x squared plus 24 minus 3x to the negative 4. And let's say that's what I was looking for. Well, then you would just write your answer like so, and just bringing back down that negative exponent, and that would be my third derivative. So it's just for you to know that you can't jump from the original function to the third derivative. You need to go through the process of finding the first, then doing the rate of change on that. Okay, so that to me was a simple higher order derivative for the fact that this was just a polynomial. And be careful, don't happen what just happened to me. Make sure you rewrite the function first so that you can take the derivative without any roadblocks. Okay, so let's look at the second example. The second example says find d, and it says d2y over dx squared. Well, we call that the second derivative with respect to x twice. So when I look at this, I go, okay, this isn't a simple polynomial. This is something raised to a power other than 1. I go, right now, I'm looking at this, and this is my chain rule. So I go to take the derivative, dy dx, and the chain rule is the derivative of the whole of the outside. So the 3 comes in front. I drop this down by 1. I rewrite what's in here, and then don't forget the derivative of the inside. Well, the derivative of the inside is 2x plus 5. Now, I would not go right into finding the second derivative. I would clean this up a little bit. So dy dx, I can multiply 3 with 2x plus 5 because this has a power of 1. And remember, if I said 3 times 4 times 2, it's the same thing as 3 times 2 times 4. Your multiplication's commutative, so I can just switch this. So this just becomes 3 times 2x times 5. And I'm just taking a lot of steps just to make sure you're following with me. And then, as I said, I would distribute this. And look at my notation. My notation has not changed. It's all been the first derivative. I'm just rewriting it. So this becomes 6x plus 15. And then this is 6x squared plus 5x plus 2. Okay, but the question was to find the second derivative. So now I'm looking at this and I go, okay, if I want to find the second derivative, that's going to require the product rule. So if you want, some of you have been doing a very nice job making your key. You can write off to the side, f of x is 6x plus 15. F prime of x is just 6. G of x is x squared plus 5x squared. And then g prime of x, well, this one's a little bit messy. This one's a chain rule. The 2 comes in front, x squared plus 5x doesn't change. This drops down by 1 times the derivative of the inside. So that's going to give me a 2x plus 5. And then I'm going to just clean that up and say that it's 2 times 2x plus 5. And this is just me making the key. And I would I would leave it like so. This is my second derivative. So now let's do the product rule. So now I can write the notation. I'm on my way of finding the second derivative. And so now we have this. So the derivative of the first we said was 6 times the second we said was x squared plus 5x squared plus the derivative of the second we said was 2 times 2x plus 5 times x squared plus 5x times the first, which was 6x plus 15. Now, I know it's very tempting to go ahead and distribute here, but remember, we don't want to do that because if we want a GCF, we want to see what's common to both. And I see that I have an x squared plus 5x common to both, and I'm going to take out to the first power because that's the smaller exponent of the 2. I'm also going to take a 2 out because the 2 divides into the 6. So 2 times x squared plus 5x, well, that's my GCF. And then what's left is this becomes 3. This crosses out to just give me 1 x squared plus 5x. Plus this 2 crosses out this crosses out completely, and I'm left with 2x plus 5 times 6x plus 15. So we have this. So as you can see, this gets a little maybe complicated, but it should be easy to follow as long as you're careful with your GCF. This is the piece you always want to clean up. The GCF you don't do anything with. So here, when I distribute this becomes 3x squared plus 15x plus, and this you actually have to double distribute, and you get 12x squared plus 30x plus, so that's 30x, and this is going to be another 30x, and this is going to be plus 75. And so in here, when I'm done, and I'm going to combine, 3x squared and 12x squared gives me a 15x squared. A 15x, a 30x, and a 30x gives me a 75x plus 75. And my final answer for this higher order derivative, I could leave like so. All right, if you went ahead and distributed, you could, but that's where your final answer would be, okay? All right, so those were your derivative tables. Those shouldn't be terrible, maybe just a little bit on the tedious side, but we have derivative tables coming up, sometimes also known as symbolic derivatives. This is very big on the AP exam. So what happens is they don't give you a function that you can take a derivative of. They give you a table, and they give you the table of values of the original function and the derivative values. So I call this a derivative table. And then they told me h of x is equal to 2f of x plus g of x. And they're asking me to find h prime of 1. So they want me to take the derivative of h and then evaluate it for when x is 1. Okay, so here when I'm looking at this, I always want to see each term. This is a polynomial. This is what I call the most basic idea of the derivative table. If I look at this, I don't see any chain rule because I don't see anything raised to a power than 1. I don't see a quotient rule because I don't see anything division. I don't see two functions being multiplied together, so it's not a product rule. And the last one that's pretty hard to tell is a chain rule. That in this case would be one function, let's say g of x, within f of x, but I don't have any of that. So this is what I call my simple polynomial that I'm just going to take the derivative. So when I take the derivative of h, this is just a constant multiple rule. That doesn't change, that stays 2. Well, what's the derivative of f of x? Well, we know it's f prime of x. And then what's the derivative of g of x? That's g prime of x. So now we did it. We took the derivative. We just want to evaluate it for wherever I see x. I'm going to take x out, and I'm going to replace that x with the one that they want me to evaluate it at. So when I go ahead and do that, I'm going to get f. I'm going to look at my table. What's f prime of 1? F prime of 1 is 4. So I replace that with 4, and I bring down that 2. And then g prime of 1, I'm just looking here. G prime is right here, and of 1 is 15. So it's plus 15 equals, so now we're just evaluating it. This becomes 8 plus 15, so 23 is h prime of 1. Okay. So hopefully that one you understood. I'm going to stop this video because I'm going to get cut off, and I'm going to start the next one. So just stay tuned for a couple more problems.